I'm going to spend the last 10 minutes of this lecture hour on the beginning of this new topic. Thank you for your inputs on the question grading. I promise you, when any of you have to do, the purpose of exams, you might think, is to evaluate you. But that's the secondary purpose. The main purpose of exams is educational, for you to learn what you know and what you don't know. Okay? And I think probably that this exam served that purpose very well. And it'll also help you on preparing for the final. The process is painful for all of us. All right. We are now going to talk about the three-dimensional images in this last section of the course. And lots of the images that we have in medicine are three-dimensional because they're about the body. Okay? But some of the things we're going to talk about, in fact, pretty much all of them, will also apply to two-dimensional images in a certain way. But the basic idea is that if you have a three-dimensional image of my body, and if I want to compare it to a standard body, I may have stood this way in the three-dimensional image, and in order to do the comparison, I have to rotate the image. Or I may have stood over here in the imaging device, and I need to translate me to over there. Or I may have been at a point in my daytime fluctuation of weight that has made me expand a little bit because I just ate, right? Or just because I was in a different imaging device that had a slightly smaller tunnel in it, I might have had an expansion. And to compare images to images, whether you want to do statistics on images or you want to do diagnosis on the basis of various properties in the images, you need to get the images into comparable positions, orientations, and scales. And so we're going to be talking about these geometric transformations. And they fall into the categories that I have listed here. There is a set of transformations, and now when we talk about transformations, we're talking about really transformations on the coordinate system. So you have positions in the space X. And we're going to talk about geometric transformations T of X, where T, if it's geometric, might be expansion or contraction, it might be shifting, it might be rotation, or it might be distortion, deformation. And we're going to understand these into, first of all, two categories. The first category is T of X is AX plus B. The first thing you have to learn is that those aren't linear. Would you believe? Why? Unless B equals 0. Because A of 2x plus B is not the same as 2AX plus B. It's 2AX plus 2B. Okay, so these are called affine transformations. They are not linear transformations on the space. And there are transformations that are called rigid, which means that nothing is expanded or contracted. So you can shift. If I shift my hand, it's still the same size as it was. If I rotate my hand, it's still the same size as it was. And so we have rotation and translation that are rigid transformations. And translation's easy to apply, right? We just add a constant to x, a constant vector to x. Translation x, we simply add a constant vector. It's affine with the A being the identity matrix, right? But rotation is painful, more painful in 3D. And we know already how to do it with the rotation matrix. But computationally, that turns out to be a crummy way to do it. It's hard to understand and how to figure out what it ought to be. And there is a different way of looking at it that has to do with understanding every rotation has an axis and a angle of rotation about that axis. And that way of understanding it yields a very interesting mathematical representation of rotations that is called quaternions. And that's the computational method that you're most always going to want to use in both thinking about and applying rotations. And so we'll talk about that. There are the so-called similarity transformations. It's similar in Euclid's sense. You know, similar triangles that you learned about. In this case, similar pyramids or whatever. And they consist of rotation, similarity, have rotation, translation, and scaling, uniform scaling, but not non-uniform scaling, not scaling that's different in different directions. And so, in general, A, for an arbitrary transformation, consists of a rotation, non-uniform scaling, and another rotation. But non-uniform scaling is not allowed in a similarity transformation. That's a kind of distortion. Okay? And so it's a subset. A's that implement similarity transformations have a subset of these where the gamma, all the non-zero diagonal elements in gamma are the same. That's uniform scaling. If you have 7, 7, 7, 7 as the diagonal elements, then a bunch of zeros, that's non-uniform scaling. So that's uniform scaling. Okay, so those are similarity transformations, and those are very much of interest. And we'll see that the quaternions don't admit translation, but they deal with the uniform scaling and rotation. The next way of understanding this, the math for this, has to do with perspective. And perspective basically means that things that are farther away appear smaller. So in the imaging process, you have this effect of depth on your image. So Scott back there appears a lot smaller to me than in my picture than Alan does up here. Right? And radiographic devices also have that property. If you the things that are more distant from the X-ray tube appear smaller. And so we have to be able to handle that and account for it. And it turns out the way we handled it is using something called homogeneous coordinates, which essentially turn operations that are given by 3x3 matrices into operations that are understood in terms of 4x4 matrices that are said to be in homogeneous coordinates. And it turns out that they're also useful for applying similarity transformations. The last thing is distortion, right, where T is not affine. Different parts of the images are stretched different amounts, or rotated different amounts locally. And we need to be able to think about that. And that's what this section of the course is about. It's about computing all of these transformations, typically in such a way as to bring one image and another image into some kind of registration so that we can compare them. Okay? And so we're going to start with quick understanding of rotation, of translation, and then we're going to go on and spend most of our time on rotation. And in doing so, there's going to be a section on quaternions. And what I want to point out is that there is a, not only this set here, where is it? But there's a slide set from Tom Fletcher, somewhere here I reference, that focuses on the quaternion approach. So there's two slide sets for this section. There's this one and the other one from Fletcher. Okay, till next time.